Hi everybody, thank you for coming to watch this Canyon Academy Physics video. In this Physics 112 concept video, we are going to be covering the concepts from week 12, which include early atomic models and the atomic line spectrum. So the first thing that we're going to talk about today is the early atomic models, and there were some models that predated the models that we're going to talk about today, but it wasn't until the late 1800s that significant improvement was made in the atomic construction. And so the plum pudding model is what we're going to talk about first, and this was proposed by J.J. Thomson. And the plum pudding model believed that the atom was made up of a volume of positive charges that were just coupled with negatively charged electrons scattered throughout. So there wasn't any true layout for the atom that was believed, other than that just these charges of positively charged particles that they could not define, and the negatively charged electrons were just coupled and scattered throughout this large sort of mess here. And so it wasn't until 1911 in Rutherford's gold foil experiment that the nucleus and the electron clouds were determined. And so the gold foil experiment was just basically, we can see this sort of diagram below. But the gold foil experiment consisted of alpha particles that are just positively charged particles that were fired in the direction of a very thin gold foil. And once these particles interacted with the atoms of gold in this foil, they observed that there were some particles that traveled. They were backscattered from the gold foil, whereas a majority of the particles traveled straight through. And so what they predicted was that at the time, they believed that solid matter at the atomic level was meaningless. And so they believed that just a majority of these particles would obviously go straight through, and they would only be deviated a little from their intended path. And this was because of the electric field of the atom. But what they observed was this backscattering, like I said, and this was new to them because they didn't believe that there was anything for these particles, these positively charged particles, to interact with and bounce off from. And so what they concluded was that the atom must contain a large concentration of positive charge at the center, and when the positively charged particle interacted directly with this positively charged nucleus, is what they termed it, then they were going to backscatter. And so this is what we see here from these red lines. And then obviously, since a majority of these particles did travel straight through, they believed and they proposed that the atomic model was mostly consisted of empty space. And so there are some problems with this model, and that's what we're going to talk about next. And so the first problem with this model is that it can't really explain how the atom remains stable. And what I mean by that is that if we have electrons that are in electron clouds, like they said, that are just orbiting and rotating, then they must have some sort of acceleration. And what we know from previous weeks is that whenever we have a charge that's accelerating, then it must emit electromagnetic radiation and create electromagnetic waves. And so if these electrons are emitting radiation, then that must mean that they're losing energy. And so what you can see from this dotted line is that this is the projected trajectory for these electrons once they're losing energy. And so there was no understanding of how these electrons could remain stable in these orbits if they were losing energy, because it was believed that they would just spiral into the nucleus. And so the second problem is a little bit more difficult to understand, but hopefully you'll have some more context to it once we talk about line spectra. But that is that there was a lack of explanation also for the lines that were observed in both the absorption and emission spectrums of gases. And so we're going to talk about absorption and emission spectrums after we get into how Niels Bohr improved Rutherford's theory of this sort of planetary construction of the nucleus and electrons. And so Niels Bohr improved upon Rutherford's theory by suggesting that electrons existed in fixed orbits where electrons could move from one orbit to the next. And like I said, it might be sort of difficult to draw how Niels Bohr's model fixed these problems. But Niels Bohr models was based on the assumption that the electrons would not deviate because they were held stable by Coulomb's forces. And so basically what Niels Bohr determined was that electrons are capable of moving from their current orbit, but it requires the emission or the absorption of energy to do so. And so each orbital that we're talking about here, we have a higher energy orbital and a lower energy orbital. Each orbital possesses their own energy potential, and this energy potential for each orbit is unique to each atom, and that's very important to understand. And so I have a definition here. It's that the ionization energy, and the ionization energy is the energy that's required to excite this electron. So put it into a position where it can transfer to a different energy, to a different energy orbital. And so in order to transfer this electron to the inner energy orbital, you need to emit energy, and that's true for whenever you're going from a higher energy orbital, which are the outermost, to a lower energy orbital. You must emit energy as a photon, and so that's what's drawn here. We have this electron, and it's emitting a red photon with a certain wavelength. And so if this electron, once it's transferred to this inner shell, if this electron desires to go back into the higher energy orbits, it must absorb energy as a photon, and this photon must have the exact same wavelength as the one that it had emitted. And that's because this whole entire concept has to follow the law of conservation of energy, and that energy cannot be created or destroyed, and it's only transferred. And so in order to gain the energy that it had emitted by transferring to a lower energy orbital, it must regain that energy, the exact same amount of energy. And that's why discrete colors of light are required for an electron to jump up or down. So if this was a red color photon, then that red color photon has a very specific wavelength, and therefore it has a very specific energy. So if it were to try to absorb a yellow photon, then it would not be able to absorb that, and thus it would not be able to transfer to the energy level that it had left earlier. And so other colors, like I'm trying to say, is that other colors may not have the right ionization energy to cause the jump, because we know that a yellow photon has a different wavelength than a red photon, and therefore has a different amount of energy. And so next we're going to introduce atomic line spectrum. And so like I was saying earlier, this all starts with a certain amount of energy within the atom or nucleus, and so this amount of energy is conserved, like we just talked about. And so whenever we have a photon of a certain color that is absorbed, it must that same wavelength of photon must be ejected in order to emit electromagnetic radiation. And so whenever an electron emits electromagnetic radiation, we can observe that on a spectrum. And so I have a definition here, and that is a spectrum is an assembly of energy levels in the form of radiations emitted by an atom in its excited state. And so this is very specific to every atom. Every atom has their own discontinuous line spectra, and each line on the spectra corresponds to a specific wavelength. And so that means that these wavelengths and the discontinuous line spectrums are going to be unique to every element. So we can actually look at a spectrum, an emission or absorption spectrum, and identify which element that is. So if we consider hydrogen here in the emission and absorption line spectrum, we know that because these wavelengths are present at these spots, then we know that that is hydrogen. So that's how we can use the emission and absorption spectrum. We can use that to identify elements. And so lastly, what I want to talk about is just sort of a continuation of atomic line spectra. And so one important note here is that a photon emitted or absorbed is equal to the difference of the initial energy level minus the final energy level. And so we have an equation here that is EI minus EF is equal to Planck's constant times frequency, or the change of energy is equal to Planck's constant times frequency. And so like I said earlier, this radiation can only be emitted when an electron jumps from one orbit to a lower orbit. Because when an electron emits that energy, it is going from a higher to a lower energy level. And so if we want to find the energy of an electron at a certain energy level, we can determine that by saying, by using this equation, E quantum number n, so whatever shell it's at, is equal to negative 13.6 electron volts over the quantum number squared, so the energy level that it's at squared. And so lastly, You might have seen this equation before, but this is used to calculate the wavelengths of spectral lines. So when we have that emission spectrum, we can calculate which wavelength it's at by considering what energy level it started at and what energy level it ended at. And so this is the inverse of wavelength is equal to Rydberg's constant times 1 over the initial energy level squared minus 1 over the final energy level squared. And so earlier I'd shown a picture of the hydrogen emission spectrum. And so these are some important notes for the different series in this hydrogen emission spectrum. So the Lyman series, you might need to know this, occurs when this should be, I want to make a note here, that this should actually read N final. So N final, when the final energy level is 1, 2, or 3, it's going to correspond to either one or three of these series. And so the Lyman series occurs when the final energy level is equal to 1. So it's in the innermost shell, and this results in a wavelength that falls in the UV region. And the Balmer series occurs when the energy level that it ends at is 2, and this results in a wavelength that falls in the visible spectrum. And lastly, as you can see here, the final series occurs when NF is equal to 3. The final energy level is equal to 3, and this results in a wavelength that falls in the infrared region. And so the very last concept that we're going to cover is just de Broglie wavelengths and how we can actually determine why these quantum numbers are as they are. And so we can see from this diagram here that only a whole number of wavelengths can result in constructive interference for this atomic model. And so that's where we observe that the principal quantum number n is equal to the number of waves present at that shell. So we can see how for n there's only one wave. Actually, it's a little bit easier to see from energy level 5. So at the fifth quantum number, there are 5 waves that are actually present. And so this is just basically the completion of the concept video. In this video, we covered the early atomic models and the atomic line spectra. So if you have any questions, feel free to leave them in the comments below.